2009. So this is our 11th year. And the team is very small, and it's a mix of computer science and software engineers and people with geospatial data expertise. And our funding from the National Science Foundation comes from the geoscience part of NSF. So our core focus are on things like applications of high-resolution topography to processes like earthquakes and volcanoes and geomorphology and surface change related to natural processes. But Chelsea will show you a bunch of cool anthropogenic examples as well. Next slide, Chelsea. So OpenTopography provides a suite of different kinds of services to our community and to the broader kind of geospatial world. That includes the data hosting and distribution of data. So we have partnerships with a whole variety of groups, both within the National Science Foundation, but also more broadly, groups like we've worked with various state entities. We're the sole distribution pathway for all LiDAR point cloud data collected by the New Zealand government as part of the national mapping effort. I'm giving a talk at EGIC on Wednesday on the topic of distribution of the USGS 3-depth LiDAR data set. So this is, many of you are probably familiar with 3-depth. It's an effort by USGS to collect nationwide LiDAR to produce high-resolution DTMs and DSMs. OpenTopography now provides access to all of that data set. So it's about 65% of the United States. We'll be talking more about on Wednesday in the LiDAR special topic session, I guess. And then we do a lot of education and training, both in-person short courses previous to the pandemic and now things like this online. And as I said, we've worked with lots of different entities, both within sort of academia, so the NSF kind of funded world, as well as these state and local and international groups that are collecting data and need a place to put it to make it accessible to their broader communities. Next slide. There it goes. So, as I said before, the goal of OpenTopography is really to make it easy to access LiDAR initially, but also other types of topographic data in a way where a lot of the computation is performed through a web browser or through an API on a variety of computing resources at the supercomputer center. So this is the ability to kind of arbitrarily make area of interest selections on, say, raw point cloud data and quickly derive a DTM as well as a visualization or some other GIS derivative product and download just that product that you need. So we provide access to everything from raw point cloud data. There's something like 25 trillion LiDAR points accessible through OpenTopography if you include the 3-depth data. We also have a whole bunch of kind of what we call standard DTM and DSM products, and then we also provide access to global data sets like SRTM, ALOS World 3D, and GMRT, all these kind of more lower resolution, sort of 30 to 90 meter global data sets, and those are accessible via a web browser as well as through the API. And so this differencing work that Chelsea's going to show you is just one sort of example of the suite of processing tools that OpenTopography provides. Just to give you a sense of who uses OpenTopography, it's gotten to be a relatively large community over the 11 years or so we've been around. About 130,000 unique users, about up to almost 1.5 million jobs run to either process or download data. Our core community remains academic users, but the diversity has grown quite a bit over the years, and we have quite an interesting group of users who are taking advantage of these data sets for kind of things you may not have initially expected. So things like virtual world development, say video games and other kinds of immersive online experiences, lots of kind of GIS, geospatial types of applications, people using OpenTopography source data for 3D printing and all kinds of other interesting applications. So that's kind of the overview of what OpenTopography does, and I'll hand it back over to Chelsea unless there are any questions about kind of OpenTopography at the high level before we dive into the differences. You can ask those, I guess you can chat those questions. Is that the most efficient way to do this? All right.
Well, fun. And again, feel free to chat questions as I'm talking, and you can bring up any questions about OpenTopography in general towards the end. So today we're going to be speaking about topographic differencing. So generally, high-resolution topography is a powerful observational tool for studying the Earth's surface. And a recent very cool technology is topographic differencing of multi-temporal topographic data. This is used to detect surface change. Recently, OpenTopography added on-demand vertical and 3D differencing. Today, we're going to show you how to use these different tools. Particularly, we'll be discussing the next generations where we can learn about GIS from using these tools, discuss with 3D vertical differencing, and then discuss the slightly more technical side of some of the cyber infrastructure challenges that we had to overcome to add these 3D and vertical differencing tools. And we hope that you will all participate in the demo where I'll show you how to use these tools on OpenTopography. So here is a map of all of the topography data in the US that is available from OpenTopography. The red data sets are the data sets that are hosted by OpenTopography. And so we've implemented the differencing tools on the overlapping red data sets. The green data sets are the USGS 3-depth. So a lot of cool next generation science that can be done with the multi-temporal topographic differencing, and I'll highlight some cases today. Currently, we have it implemented on over 60 data set pairs that show a wide range of natural and anthropogenic processes, and the applications are numerous, including those in natural hazards, urban development, forest structure, and river erosion. So we've added 3 different types of topographic differencing into OpenTopography. One is this case on the left here. This is vertical differencing. We start with data sets that are in point cloud form. For example, this shows sand dune migration in New Mexico. Second, we have vertical differencing that starts with data sets that are originally in raster data set or raster format. This shows the Kilauea eruption in Hawaii. So the first part of the talk will focus on vertical differencing, where you could generate either of these 2 plots that we show here. And then we have a third type of differencing. This is 3D differencing, detect the horizontal and vertical displacements of the Earth's surface. And those are shown here by these arrows, show horizontal, and then the blue and red colors, which show the vertical motion. So we'll discuss the 3D differencing in the last part of today's session. So here is some terminology that we use for vertical differencing and for 3D differencing. So the first data set that was acquired is the compare. Second data set that was acquired is the reference. So here for the sand dune case in New Mexico, first data set or the compare was a September 2009 data, and the reference data set was collected later in June 2010. And then we can do vertical differencing. The results are shown here, where blue shows subsidence or erosion of the ground surface, and blue shows deposition or uplift. So question to the audience, these are sand dunes. You can see that they've moved. Based on these colors, what is the sense of motion of these sand dunes? So feel free to chat your answer.
Or you can put that another way and say, which direction is the wind blowing from? Or the dominant wind direction?
So is the wind blowing, for example, to the southwest, to the northeast, northwest? can't see in chat, but I can hear a few people typing.
And nothing in the chat yet. I'm monitoring. Here we go.
There actually is. I didn't let folks know that when the way that the chat is set up, it defaults to just texting me or just to chatting with me. So most folks said to the Northeast. You guys all can have the choice of sending your message to all participants, I believe, or to the panelists. So you should be able to do that.
Now we're seeing some Northeast. It seemed like people must have been sending this to you.
Yes.
It was a little confusing.
You see here, based on actually both the topography and the differencing results, that the wind is blowing to the northeast. Great. Thank you for participating. So we'll get into a little bit more details about how topographic differencing works. So we often start with a point cloud of both the compare or pre-data set, and then a point cloud of the reference or post-data set. It's often the case that the reference data set will have a higher resolution or higher point density because, or due to advances in sensor technology over time. So then we grid both of these topography data sets onto identical grids. So they have the same resolution and the same boundaries to the grid. The next step is to then perform topographic differencing. So it's a raster subtraction of the reference minus compare. And we see here that the red shows downward movement and the blue shows upward movement. We also offer options to mask out areas that are below a certain error threshold. So if you know that displacements below a certain level, say 20 centimeters, are not significant below the noise threshold, then they can be masked out, in which case they'd be, for example, shown in gray. So in the topographic differencing workflow, we require that we begin with overlapping data sets. Data sets are then gridded to identical grids. You can do this with data sets that are either in original raster or in gridded raster or point cloud form. And we can work with data sets that have varying raster and point densities. Currently, we do require that the data sets are in the same coordinate system. Perform a raster subtraction, and we offer user the option to define an error threshold. And again, points that are below this error threshold will be masked out and shown in gray. And then OpenTopography will display the difference map of the differences, as well as a histogram of the differences. So this plot here on the right shows infrastructure damage following the 2016 #7 Kumamoto earthquake in Japan. So you can see here will be a red house, and this represents a house that unfortunately fell or was heavily damaged during this earthquake. So what are the challenges and requirements? So we work with legacy data sets. These are data sets that are typically older, have much lower resolution, and sometimes much higher noise than modern data sets. However, they become absolutely valuable following an event of interest because they're often the only pre-event data set that we have. But it's very important to look at the metadata very carefully, for example, to understand what is the coordinate reference system of that particular data set. So when we originally, another challenge is working with hybrid data sets. So we originally built the the differencing to work both with point cloud and raster data sets, as well as data sets with varying resolution and shot density. And we are currently adding larger implementations of the differences, for example, to terrestrial laser scanning data, structure for motion, and global raster data. The algorithms must work on demand and with different data types, currently have a very low failure rate, again showing that our algorithms can ingest these different types of data and successfully produce a differencing output. And in terms of the cyber infrastructure, the differencing must interact with the current high-performance computing system that OpenTopography uses at San Diego Supercomputer Center. This graphic here on the left shows the 2018 tornado eruption in Hawaii. Now we'll go over some examples of the topographic differencing. This shows results differencing at Salt Lake City Airport in Utah, where over a 2-year period, we see the airplanes have changed position. And so we see airplanes in different colors for the topographic differencing, reflects where airplanes were at each of the different LiDAR acquisitions. So an example that shows rock falls in Yosemite National Park in California. We see the 2 topographic hillshades, and in this area we see a rock fall and tree fall in differencing product that looks red, indicative of the rock mass that was lost between 2006 and 2010. This shows that we can use topographic differencing to look at natural hazards in national parks. We implemented topographic differencing on a number of critical zone observatories. This is an area in Crosby, South Carolina that had extensive land use due to agriculture and water degradation. So the question is, how does the landscape recover? We can use topographic differencing to look at the seasonal changes in vegetation, other aspects of the landscape. Looking at the difference between summer and winter. So this is another example in Salt Lake City. And then the differencing, the thing that jumps out at you are all these houses that are in blue. This shows housing developments that were built between 2016 and 2017. So topographic differencing really makes it highlight urban growth in different cities in the West. So this is an example looking at Iowa City between June 2008 and August 2010. The differences you see are a change in the level, decreasing river level, as well as some infrastructure development here, which is at the University of Iowa. So a question you may be asking right now, where can I perform differencing? Well, we've implemented differencing on over 50 dataset pairs. The datasets hosted by OpenTopography. Many of these examples are in the US. We also have differencing on several international datasets. One of the cool areas to look at is Salt Lake City. We also have differencing implemented on a number of critical zone observatory datasets, rivers and riparian zones, natural hazards, include the creeping landslide Colorado, rock falls in Yosemite, 2018 tornado eruption in Hawaii, the 2010 El Mayor earthquake in northern Mexico, just felt in Arizona, and 2016 magnitude 7 Fungullion earthquake. And there's certainly many more examples to come. So we'll let you walk you through how to process a data set on OpenTopography. And here we've highlighted some very cool examples we suggest that you may try. So for vertical differencing, look at urban growth, look at Salt Lake City, release on to release off conditions, look in several data sets in central and eastern Pennsylvania. For riparian zones, there's a cool data set in Flathead, Montana, as well as Blenheim, the South Island of New Zealand, the volcanic eruption of Kilauea in Hawaii, rock falls in Yosemite. For 3D differencing, more limited application, but these three examples are very fun to look at. We have the Kumamoto earthquake in Japan, sand dune migration in New Mexico, and landslide in Colorado. We ask, however, that you do respect some processing limits requests. For example, you want to process a raster data set for vertical differencing. Please limit the size of data that you process to 10 square kilometers. For raster data sets or 20 million points for point clouds. And if you do 3D differencing, limit to 10 million points. And these limits, we just ask that you follow them during class today. If you want to process additional data sets after class, certainly feel free to process at the much larger data sets. But we do want these data sets to process fairly quickly so that you can look at them before the end of class. Are there any questions before we go on and show how, this demo on how to use OpenTopography? You can chat or and also just say them out loud.
So yeah, there's one question. Chelsea, you can see it, but I can read it to you. Does differencing processing mean a different kind of comparison between current data to historic data?
Sorry, what was, to do differencing, can you do it with historic data?
Yeah, I think that's the question. Annie, you can clarify that by chatting, by typing if you want to clarify. But I think, yeah, how about comparing to historic data?
So we have it on differencing implemented on a variety of data sets in OpenTopography. The earlier ones were around 2005.
Yeah, I would just say that there's not that much historic LiDAR data in the world since LiDAR is a relatively new technology. But if you had legacy topography data that was in a raster format, say digitized from old topographic maps or photogrammetrically derived from stereo imagery, you could certainly intercompare those data sets with LiDAR using the techniques that Chelsea's talking about.
And we'll show you where you can download these topographic data sets on OpenTopography, which can be fully downloaded. And we also, yes, OpenTopography does host OpenTopographic data. So we want you to go to this link that we just posted. No, all participants. To go to OpenTopography.org. Again, please feel free to chat any questions that you have. We do this workshop in person. We do walk around to make sure that people are following along. We obviously can't do that here. But again, please feel free to ask whatever questions you have. And Annie says, and how to do the processing. So we'll show you where we keep, you can actually find the tools that we use. They are all open source. For example, for the vertical differencing, we use GDAL. And for the 3D differencing, we use a iterative closest point open source tool, which I'll discuss in more detail shortly.
Yeah, but the clarification is that this only works, basically the tool that Charles is going to show you, it only works if the data are hosted by OpenTopography. So they have to basically be on our servers for this to work. And certainly we don't have every data set on Earth, especially ones you're producing on yourselves, say. So OpenTopography provides the data and the tools in the case of data hosted by us. But if the data is not hosted by us, you could still implement the same process that Chelsea's talking about. You just have to do it locally on your own machine using, a GIS environment of various types, whatever your preference is, ArcGIS, QGIS, open source tools like GL.
Yes. All right, so has everyone gotten to OpenTopography's homepage? So for future reference, if you'd like, you can set up an account by going to My OpenTopo to ultimately allow you to process larger data sets on OpenTopography. But for the size of data sets that we're asking you to process today, there's no need to set up an account. So you can go to Data here, so click this Data button. So will then take you to this page where you can see all of the topography data sets that are hosted by OpenTopography. So for today's demo, I'm going to show the example on the Kilauea eruption in Hawaii. But again, feel free to do the demo on any number of other data sets, specifically the ones that I listed a few minutes ago, or follow along and repeat the exact step on the Kilauea area.
And so that's not everybody's experience is like mine, but I'm seeing it lags a decent amount, so just be careful not to get too far ahead of people.
Okay, thank you, Chris.
Yeah.
So we're going to zoom in to Hawaii here, and that shows these different data sets in red. And we're going to then go here to select a region. And then that lets you come and click on an area where you want to perform topographic differencing. So and then we put our box over this area, we can then zoom down. And this first window, we see high resolution topography data sets that are hosted by OpenTopography. The Kilauea eruption in July 2018, June 2018, and then the Hawaii Big Island survey. And if you come to the right, you see that these first two data sets have differencing enabled. You can also see, if you prefer to simply download the data, that these data sets are available in both point cloud and raster formats. So, because we're interested in differencing today, let's click the differencing tool. So that will then take you to this page that says Topographic Differencing. And for this data set, we have three different options of differencing. Differencing that starts with raster, vertical differencing starts with point cloud, and 3D differencing. So we typically recommend that you do the differencing starting with raster. Generally, it's faster. You can also perform it on larger data sets. And we allow people to perform differencing of digital terrain models versus digital surface models. You'll want to click on Start Differencing. So then take you to this raster vertical differencing page. And you want to select the dataset area where you want to perform topographic differencing. So just make the selection, come up here to select a region, and then put a box over a certain area. It will zoom down. You can see the area that we selected, so it's approximately 7 kilometers. So we asked today that you process areas that are less than 10 kilometers, so 7-kilometer area is fine. Then look at some of the other options. These data sets exist only in digital terrain model format, so that's all we can use for the raster differencing. For example, there's no DSMs. We can enable an error threshold to allow us to mask out areas that are below the level of detection. We won't do that for today. And then OpenTopography will generate topographic hillshades of both of the areas, and you can select both the altitude and the azimuth of light. So put in a title for the job. I'll put in Hawaii. You can add a job description, and you do have to enter your email address. So once you've done all of this, you can press submit. You'll see that the differencing job is currently being run, in fact, at San Diego Supercomputer, and this gives you an update to the steps that are being performed in real time for your topographic differencing. And when this is done, then you'll get an email. It'll actually link you back to this page so you can retrieve the processing results. Are there any questions?
It does appear that there are several jobs running at the moment.
Excellent. Annie says, how is the resolution of the data? So most of the LiDAR data sets are, say, half a meter to 4 meter or so resolution. And we do incorporate that information into the default resolution of the topographic differencing. Are there any more questions?
I guess while we're waiting for that to run, I'd just say that, so this is, what you're seeing here is basically real-time updates on the workflow. So that web interface just allows you to parameterize that workflow. It's now executing on compute resources in San Diego in real time. And if you mouse over that duration NA button on your screen there.
Would you say?
If you put your cursor over that NA button where under duration.
Yeah, so when it finishes where it says duration, you'll be able to see the total time.
But if you actually click on it right now, you'll see where it's at status-wise.
Yeah, so you see that it took about 6 seconds to query the original data sets and not quite 2 minutes for the topographic differencing. Because we started a small job, and now it's actually already finished. And so you can download data, raster products, differencing products, And then come here for the visual or for the differencing result. You can see these areas in red, ground surface moved down due to the erupted material during the eruption.
It looks like, sorry, I have an administrative view, so I can see what jobs are running in OpenTopography in real time. So I'm watching the dashboard. It looks like most of the people who ran jobs have finished. There's one left visualizing and one stuck in the full vertical differencing. So
I give the rest of the presentations, and then we can look at the results at the end. We do want to make sure that people who are interested did get a job started. So if you are still having trouble with that step, please chat and Chris can help you.
Yep.
So we also implemented 3D topographic differencing in OpenTopography. These are results from an earthquake in 2016 in Japan. It's a magnitude 7 earthquake, so it's similar earthquake to what could happen along the San Andreas Fault in California. These are the results. The colors show the vertical displacements. The arrows show the horizontal displacements with these pink error ellipses. So we perform 3D topographic differencing using open source implementation of the iterative closest point algorithm. So we perform this algorithm on windows of topography, typically LiDAR data sets. For example, here this shows the compare or the pre-data set, which is in blue, and the reference or post-data set, which is in red. And the iterative closest point algorithm works to iteratively align the windowed pieces of topography. So you can see here, top right, this animation shows that the blue data set progressively moves towards the red data set and is aligned after 13 iteration steps. The alignment is done with a rigid transformation. So this includes a rotation and a translation. You take the undeformed point cloud, apply the rotation, and then the translation, and that will generate this deformed point cloud, which you would want to align well with the post-earthquake data set or post-event data set. Here's another example, another slide showing how this works. So again, we take windowed data sets, the compare and reference data set. The resolution of the topographic differencing is often quoted in the dimension of the window of the compare or the pre-event data set. And we'll discuss this in a few more slides, but it's typically on the order of a few tens of meters. Do the ICP alignment of the two data sets, and then when this approach is applied to a very large, for example, LiDAR survey, then we generate a 3D displacement field. Again, this shows the horizontal and vertical displacements. So here is the workflow showing how we've implemented this 3D differencing in OpenTopography. Like you saw for the vertical differencing, the user has to select an area with overlapping data sets and has to decide to perform 3D differencing. We offer processing options to include and either based on the point density of the data set We offer the user the option to work only with certain point classifications, for example, to perform differencing only with ground classified points. We do impose processing limits to make sure that the job doesn't take a very long time to run. And finally, or towards the end, we do 3D change detection, where we window the point cloud data sets, and we use an open source ICP algorithm to compute the 3D displacements and rotations. Finally, we present the results, so users can download GeoTIFFs of the 3D displacements and rotations, and graphics of these results are shown on this output window in OpenTopography. So I'll discuss in more detail how we make suggestions of the ideal window size or resolution that are based on the point density of the data set. And then I'll also discuss how we looked at several different ICP algorithms before selecting the ideal one for differencing in OpenTopography. So we wanted to determine the best window size for data sets with varying point density and also varying error. So these, we did this based on synthetic testing. So we split data in half and artificially offset one of the data sets. And our question was then, how well can we get the known displacement back by using the iterative closest point algorithm? So this plot on the left shows displacement error versus window size for a 2012 data set in Indiana with a point density of 0.6 points per meter squared. And we see here that as we increase the point size, or essentially the size of the window that we're using for the 3D differencing, the error in the displacements does decrease. And this is expected because when we have a larger window size, there's more features to use for the alignment. On the right shows the same experiment, but for the 2014 Utah data set with a much higher point density, in this case about 8 points per meter squared. And again, we still see that error decreases with increasing window size, but in this case, the error decreases below this 20 centimeter error threshold at about a window size of about 25 meters. And so we make 25 meter the suggested resolution for the 3D topographic differencing for this Utah data set. Yes, in summary here, we see that data resolution and quality impact the ideal window size. So we ran a similar experiment for many data sets that are hosted by OpenTopography with some artificial thinning. So this shows the optimal window size versus point density. And we see that data sets that have a higher point density can have a smaller window size, in other words, a better resolution. And so we use this equation here at the top, which relates point density to window size to make the recommended window size to the user. So if you decided to perform 3D differencing, a few minutes ago, this equation was used to generate the suggested resolution. We also looked at the different types of iterative closest point algorithms. There are several different classes. There's one called point to plane, and this aligns the compare points with the reference surface. The second option is this point to point option, which aligns compare and reference points. And we looked at several different implementations, including this library for ICP, and then the PL option. We looked at these examples in Japan, the expectation that we wanted the differencing results to change along faults where we expect changes in displacements. We may see topographic displacements that correlate with flight lines that again reflect errors in the LiDAR data, but we don't expect earthquake displacements to change along different landscape types. We ultimately preferred this Lie by CP point to plane option, where the topographic differences are concentrated primarily along these topographic faults, which are shown in black. There were 2 point implementations that we tested, but in these cases we see that they both have strong correlation to land use, which again we wouldn't expect in an earthquake. So we implemented the topographic differencing on OpenTopography using this Lie by CP point-to-plane implementation of the iterative closest point algorithm. So I'll now walk you through several examples. We do 3D topographic differencing to really make the assumption that the landscape shifts laterally. In other words, it maintains its shape. And so really can only apply topographic differencing to processes where this is the case. One example here is the Fungullion landslide in Colorado. Here is the active landslide. This plot here is capturing landslide creep from July 3rd to July 10th over a week in 2015. And we do see these clear downslope displacements here in the area of the active landslide. This example shows the Kumamoto earthquake in Japan, where we see clear offsets along, there are differences in offsets along these one fault here, and then a second fault here that was activated during the earthquake. And then finally, this back to the sand dune migration in New Mexico. And in sand dunes, or yes, you guys earlier identified correctly that the wind is blowing to the northeast. But again, we can show that here in the ICP displacements that show that there is some noise. In general, the arrows are pointing to the northeast. And the sand dunes are a little bit of an unusual case because we don't expect that the sand dunes are just laterally moving as they migrate, but in fact, they generally keep their shape. And that is why 3D topographic differencing works and is able to capture the direction of wind or sand grain movement during these windstorms in New Mexico. That is the end of my presentation. So please feel free to review data that you've processed, bring up any questions either about the data that was processed or about any aspects of the talk today. And on OpenTopography, we've also made a page where we've collected all of our resources on topographic differencing. I'm trying to add to the chat.
Yeah, I just put it in the chat actually, Chelsea, previously, because there were some people asking questions as you were talking about kind of how to do it themselves. So.
While people are thinking about their questions, I invite you to explore our website, OpenTopography.org, in more detail. We do have 3 social media pages on Twitter, Facebook, and Instagram, so please follow us on one of these social media platforms. And if you have questions about today's talk, or you're interested in working with OpenTopography to host data and ultimately to implement topographic differencing, you can either email me, my email address here, or OpenTopography at info@opentopography.org.
Thank you, Chelsea. That was fabulous, and thank you, Chris. You guys did a great job. I need to jump to another session for lunch. Chelsea, I'm gonna make you a host so you can take over if folks still have questions.
All right, great. Thank you.
Yep.
Thank you.
Thank you.
So Chris and I are happy to hang out for a few minutes and discuss OpenTopography or any aspect of the differencing in more detail.
Yeah, and as I said, I'm giving a short talk, a 15-minute talk on Wednesday in one of the LiDAR specific sessions in AGIC. So if you want sort of more of an overview of OpenTopography, and you can also get that information, hopefully, during that presentation. I also just posted, as we were going, a bunch of people were asking questions. So Chris asked a question about how to do the calculation in, say, Arc Pro, and I'm actually admittedly not as familiar with Arc Pro as I am with ArcGIS and some of the open source tools, but it's essentially just a raster calculator action of, raster 1 minus raster 2 gives you the difference map, and then getting the color map right and generating the histogram, the visualizations, and all those kinds of things are pretty straightforward. But I put a link to a YouTube video from a short course we did several years ago that talks through the basic raster math calculation. In this case, it's actually to calculate, the example is to calculate canopy height of trees, so basically DSM minus DTM. But functionally, it's the same raster math calculation. It's not particularly sophisticated. And then the other piece that I did put in the chat is a link from that differencing page that Chelsea posted, which is a link to a GitHub resource that has the actual GDAL Python script that we're running under the hood in OpenTopography to both produce the difference map, but also the visualizations and histogram and stuff.
And that is just vertical differencing.
Vertical, yeah.
Separate tools which are also on the GitHub page for 3D differencing.
Yeah. Anybody else have any other questions they want to ask, either on chat or via audio?
Well, it is noon, lunchtime here in Arizona.
Past lunchtime in Colorado.
Lunchtime, yes.
Thank you.
Meeting, and thank you guys for attending. And again, please come to Chris's LiDAR SIG presentation on Wednesday. Follow us on social media and feel free to get in touch with any specific questions that you still have.
Great. Thanks, everybody.
Bye.